Hello everyone, in today's video, as I promised earlier in the reel that I posted before, I would like to walk you through the changes of the task format of the BBE entrance exam as of the previous years, including 2024 and 2025. So in this video, I will walk you step by step through the solutions of an exam-like and an exam-based task. So these are the tasks that I make in the course based on my students' feedback or what they were asked and how difficult it was, what kind of questions they had, and then I will show you the switch from an equation and a function-based task and a text-based task. So on the exam, you will have a mixture of both for sure. And I just want to make sure that you know how to approach any of them, so you know the material well enough to be able to solve a graphical task, an equation task, maybe a task with a table, a picture, or whatever there is, a task with a lot of text. And I'm here to show you different approaches to statements, because sometimes there's more than one correct approach to a statement, and you should be able to determine which one is faster for you, which one you prefer more and you're more sure of. And yeah, so let's get to the teaching part of this video. And if you watch until the end and you like it and you find it useful, please leave a comment and like it. And if I see based on your activity that you enjoy this kind of more education heavy videos, I will of course make more of these. So let's get started. And this brings us to the teaching part of this video, where I will discuss two tasks. So one of them was added in 2025 as an update to fit the text format of the tasks, and then the task that was made by me back in 2022, but it still fit the format and the level of difficulty and the style as of 2024. So let's start with the older task first, so to say, so that you can see how it was more like before in the previous years. And of course, it changes throughout the years. If they have a lot of text tasks in one year, they can switch it up and go back to functions or to graphs. It's up to them. But what matters is that you know the theory really well, so that you can apply all your knowledge no matter in what scenario it is. Because of course, with functions, you have some certain properties, you have to know rules, how they look like. And by knowing that, you can solve basically any task about them. So let's get started. So here you have a task, and it's about two functions, one of a natural logarithm and one of a logarithm with the base of a. And this part of the task, the conditions of the task, could be a formality, so it could be very formal things that you don't really need that much. I mean, to an extent, right? Still necessary definitions for this functions, but they could be just like a formal thing, and it doesn't with no additional value, so to say, or they could really play a role in one of the answers to one of the statements. Let's say if a variable is negative or only positive, if a variable includes 0 or not, could determine if the statement is true or false. So please do not neglect this part, no matter how like formal or just like as a placeholder it seems, it could be used. So just to know, when you read the task, you should read it attentively and filter out the important information. So a task will have 5 statements that are true and false, and yeah, you have true or false next to them. And on the online format, you had like circles like this, and you had true, false. And when you clicked on the circle, it colored it, and this is how you would answer. And on the offline format, you are more likely to have like boxes. This is what we had back in 2019, because my assumption is just it's easier for a machine to check it this way. So like this, you have statements, and then you would cross the ones you think are correct. Let's see, if you think A and C are correct, you would do it like this. And it would be the same idea. So the true ones are crossed, the false ones are left a blank. But if they change the format, they will also post it on the website, and you will be notified in good time. So it's either the true and false one or the checking of the boxes one. Either way, it's very similar. And you still have to do the same calculations to either take true or false, or select the ones you think correct and leave the ones you think are not correct blank. And you don't have negative points, so even if you guess it, it's fine. And also, they don't look at the solutions, so they don't look at the thought process, and you don't get any negative marks for maybe you doing it your own way. As long as you get the answer correct, even by guessing, you still get the partial points. And the way partial points work is that, let's say we have 3 points for a question, because in mathematics, you have 13 questions together, 3 points each. So that brings us to 39% for the math part. For every statement you pick correctly as true, if it's true, you pick true, or if it's false, you pick false, you get 20% for each statement out of the points available for the question. And this is how it works. So leaving answers blank is never a good idea. Even if you don't know, even if you run out of time for one of the questions, at least guess something so that you get some partial points for that. And please, yeah, let's keep an eye on the updates of WU's website if they introduce any new formats. And if they do so, I will, of course, let you know first thing. So let's start. So here you have the 5 statements, you have the conditions of the task, and this task is short text-wise because it's more of an equation-based task. So let's walk through that. And here, sometimes you'll have 2 approaches to a statement, and you just pick the one that's faster for you or the one that you are more sure of to make sure you don't because of course there is a trade-off of doing it fast and doing it correctly. Ideally, you should do it quickly and correctly at the same time. Of course, yeah. And then with these 2 approaches that you have, for example, you have the functions ln bx and logarithm a bx, just so you have also them in front of you, in front of your eyes. If b is 1, it means it doesn't change the sign or the value of the function, so you can just kind of forget about it in a way and just write for f of x, you just write ln of x without b. You can do times 1, but it doesn't really matter, right? So you just write it as ln x, and then you see if this would hold to see if it's true or false. Then whenever they tell you to plug in a value or to do something to a function, you just follow it. So here, if they tell you to multiply it by 2, you just say, okay, 2 times f of x, that's just ln x in our case, when b is 1. And if they tell you to square an x, where x would be 2 to the power of 2. And there, here you need to know logarithmic rules pretty well to simplify it down. So there is one rule that we're using for this approach, and it is a logarithm a of x, which is equal to x. An incorrect way to remember it, so please, this is not correct, but some people say, okay, just cross out the a's and x comes down. This is not the way it solves, but it's a way that you can maybe remember it in case, yeah, the rule doesn't stick, so to say. But yeah, this is not a scientific approach. There is a different proof to that. But yeah, so here, for example, whenever you can also put 2 in front of the brackets because I'm following the rule. If it's like this, right, it doesn't matter how you format it, it's still b times c. If it's between, like, after the brackets or before the brackets, doesn't matter. So you isolate the 2 to see it a bit clearer. And then here you have ln of x is just the natural logarithm, and it's just the base of e, so to say. So this is second to the power of 2. And this becomes e logarithm e x to the power of 2. So using this rule, we just bring down this part. So we bring down the x, it's squared, it's after the brackets. You make sure you note it. And then here you bring x squared down already with the square. So x squared is equal to x squared. We got it. Another approach would be that you could use is using this rule. 1 second, so I don't run out of space to write, or just use a different color. So here, logarithm a of b to the power of r. This would be equal to r times logarithm a of b. It's a rule that you have to also memorize. And let's see if you see a rule with letters, because math stopped being easy after letters were introduced. You can plug in a few examples with numbers so you can get the feeling of the rule, so you don't forget it and you see how it works. So for example, for this rule, and this is the part where I will erase this, so I have more space to write. For this rule, what you would do is, let's compare this logarithm of 2 of, let's say, 16. That's just equal to 4. So the way that you would determine the answer to a logarithm would be, to what power do you need to put the argument to, the base to, like this lower part, to get the upper part. There are scientific names for this, the base and argument and all that, but you don't need the scientific names of these to solve the tasks, as long as you remember the rules themselves. So it's 2 to the power of 4 is equal to 16. Great, this checks out. What you could also do is, if you have it in this way, logarithm of 2 2 to the power of 4. And to what does it equal? I mean, here it's very obvious in a way, but it's very obvious, but anyway, but here what you can do to solve it is you can put the 4 in front. So you do 4 times logarithm 2 of 2, your answer, and it's equal to 4 times 1, because you need to put 2 to the power 1 to get 2. And that's how your final answer is also 4 here, like it were here. Of course, here it's a bit simpler with 2s and 4s, because some people also just know this powers of 2 by heart. But when it's like larger numbers and to the power of 10 or to the power of 15, like really that's inconvenient to calculate by hand. Putting the power in front of the logarithm, multiplying it by that is easier and takes you less time. So here what we're doing is we're taking this power, so we're following this rule, and putting 2 in front of the whole thing. And then this is where you can stop. You don't have to solve it further because, I mean, obviously they're going to be equal to each other. So sometimes once you get maybe the intermediate results or not the final result that you would like to get, that's enough already to solve a task, because again, they're not judging your solutions. They're just for you. So once you've reached a state that's enough, you can stop there to save some time for the other statements. Also here, this is when you would need to know differentiation. And differentiation is a topic that's asked on its own, so it's a separate question on the exam, and also can be asked throughout the other topics, let's say power functions, exponential and logarithmic functions, polynomials, because, well, it's a function, you need to know that function, and you need to be able to differentiate this function. So we have all the right to kind of intertwine or integrate differentiation questions into other topics. So that what makes differentiation topic that's a bit, not more important, but a bit more extensive than the others. So you should know it really well, because there could be some partial points hiding in the other topics based on differentiation and not just in the differentiated question itself, so to say. And here, so if you're not familiar with differentiation, please, of course, revise it and repeat it, because it's not covered in all school programs. And here I will give you the basics, but if you're not, like, if you want additional information, please research it just in case, so that you really understand all the rules. So here we have a function, and we want to see if we divide the derivative of f of x by the derivative of g of x, if we get ln a. So let's get started. When you have a function of x, so let's say ln of x, the basic function with nothing else, the derivative of that is just 1 over x. This is like the rule that you should memorize by heart, honestly, if you're studying for this exam. And then with the chain rule, because here, whenever you picked x, it just directly influenced the value of the logarithm. If it's 1, if it's 3, if it's 4, it directly influenced the y output, so to say. But here, if we have bx, whatever b is, let's say it's 2 times x, 3 times x, so on and so forth, you will first, let's say b is 2, for example. And my 2s looks like 3, I don't know why that happens, because I'm using a touchpad, so maybe, yeah, yes. And then you would have a function of 2x. So once you pick x as 1, or 2, or 3, it first runs through the 2x loop, and then it runs through the bigger loop of ln of whatever that is. So it's ln of 2 times 1, ln of 2 times 2, and so on and so forth, ln of 2 times 3. So you have a function inside of a function. So before getting ln of something, you first have to calculate that something, so that function. And whenever you're differentiating such functions, you would first take the derivative of the overall picture, so of the outside function, ln of dot, 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 so something. So therefore, you would do 1 over whatever was instead of x here. Now you have bx. And then you would multiply this outside derivative, it's like derivative of the outside function, by the derivative of the inside function. And the inside function is bx. And if you differentiate bx, you just get b. And here, magically, it cancels out. So b's cancel out, and even if you make a mistake and don't use the chain rule, you still can get it right, but usually it's not the case. Here just made it nice so the numbers cancel out beautifully. And the derivative of a logarithmic function, so just of a normal one, logarithm of a, yeah, this is a, not c, a of x, this would be 1 over x times ln a. And this, yes, is the default derivative for logarithm. And this is also the reason why this is just 1 over x. So all these rules about ex, when you differentiate it being ex, or ln of x being 1 over x, come from a more general rule that was before, let's say just for any logarithm. And this happens because, let's say, if ln is just the logarithm of e of x, right? If you differentiate it using this general rule, what you get is 1 over x times ln e. And ln of e is just 1. This is why this rule exists. So let's say even if you forget what the logarithm of ln x is, not the logarithm, but the first derivative of ln x, you can deduct it from the general rule of what the derivative of a logarithm is. So yeah, this is how they come to be, so to say. And then here you have, again, the chain rule. So you would do at first, the first derivative, 1 over bx, because now instead of x, you have bx, times and ln a you just keep as it is. And then you don't forget to multiply it by the first derivative of this inside function, and it's just b. And here they also beautifully cancel down. So once you have the derivatives of f of x and g of x, you just divide them. So here you have 1 over x, and whenever you divide a fraction by a fraction, it's the same thing as multiplying the first fraction by the flipped version of the second one. So it is just 1 over x times ln a over 1. And here, this is when the conditions matter. You just have ln a. But usually, normally, you can reconcile the x when you solve equations because it might be equal to 0, right? But here in the conditions of the task, we had this, scrolled up too fast. We had this condition that x is greater than 0. So it doesn't include 0. Therefore, you can cancel out the x value here and just get ln a as your answer. So it's true. Then for statement C, it's again knowing the rules of logarithms. So you have the function g of x, and it's equal to 1 at a particular x value you're trying to find it. So you say, okay, using the logarithmic properties, a to the power of 1 should be equal to bx, and then you solve for x. So you put b to the other side, you do a over b, and therefore you can see that it's false. It should be the other way around. So also these little things, like little details matter, and that's, yeah, because like if you overlook it, A, B, B, A, really easy to get confused, especially if you're in a rush, you might lose a point, and we don't want to do that, right? And then here, if b is equal to 1, so in our previous functions, now we have b1, so we just get rid of it. So it's just ln of x and a logarithm a of x. And we're trying to see what would be the y values of these functions at x equal to 1. And they're actually equal to each other because 1 is such a point where you have logarithm of e of 1 is equal to 0 because e to the power of 0 is equal to 1, right? And also the same case here for any base, essentially. I mean, apart from 0, of course, but it cannot be 0 anyway, so the problem is solved. So logarithm a of 1 is equal to 0 because a to the power of 0 is equal to 1. Therefore, both of their values are 0. Therefore, they're equal. So it's true. And the statement E is also an interesting one because it teaches you to analyze questions in a way where you learn how to spot which mistake did you have to make to put it as true accidentally. That's also like an interesting analysis skill, I would say. And here, so f of 1 over g of 1, we have ln of b over logarithm a of b. And then this would be also a very important rule you would need to know for the exam, when you change the base of a logarithm, because on your scientific calculators, it only has the input function, usually just ln or lg. This is the base of 10, this is the base of e, and you can't really pick another base that you would like to. So the rule tells you that logarithm c of b over logarithm c of a like this. So whenever you're changing a base, you can change the base to anything, be it e, be it 10, and then whatever was in the up, let's say in front of the logarithm, so b, goes on top of the function, of the fraction, and whatever was in the base goes in the denominator, in the lower part of the fraction. Also quite easy to remember. So let's say we want the base of e, so we would do log e over log e. B would go in front, in the not in front, but in the numerator, and a would go in the denominator. Also, a prettier way to write log of e is just ln. And therefore, you have this fraction here. And a mistake you could potentially make to make this to mark this incorrectly as true is if you put this on top and accidentally multiply it like that. And you're not supposed to do it, because the correct way is putting the lower part on top. So this just comes from the idea that it's, if you divide it by ln b over ln a, you must not forget to multiply by the flipped version of the fraction. So it is ln of b times ln of a over ln of b. And we cancel this out, and we just get ln a as a result, making the statement false. So yeah, one second, my camera is sometimes, yeah, perfect. Now I'm back. Yeah, so this is how you would approach such a task with equations, plugging in numbers, doing what you're told if you want a function of 0.1, or if you want to square it, and so on and so forth. So this would be a more relevant exam for 2025. Here we go. Okay, perfect. And in such text tasks, you should be able to filter out the information that's relevant and that's not very relevant for a solution. So here you have the introduction. Company A has two departments, the marketing and the finance team. Great. Then the explanation about what the marketing team does and what the finance department does is not really relevant for you. So this part you can just filter out and read very quickly and just forget about it. What's relevant is this part. So you would say the revenue of the marketing department has the following function, with 10,000 as the initial value when t is 0. So because when t is 0, it just becomes 1 and you have 10,000. And it compounds semi-annually, so twice per year. And this matters, please pay attention to this, because there is annual compounding, semi-annual compounding, quarterly compounding, and monthly compounding, and also sometimes daily compounding. And they are slightly different, like from each other. And we will get to that a bit later. And then the revenue of and then you have the next function where you actually have to build it from scratch. So here I'm teaching you the skill of reading the text and transforming the text into equation. So the revenue of the finance department has the same initial value, so f of 0, so it's just 10,000. Be 10,000. And then the revenue grows at a continuous rate of 5%. Continuous rate would involve E, so you have discrete growth with like 1.05 to the power of x, and you have continuous growth, like e to the power of something times x. Let me tell you the difference. Because here it looks normal, right? You have 1.05, it's growth, it's e continuous, good enough, but no, it's actually false. It's an attention trap, and you will have them in an exam for sure. Because whenever you're dealing with continuous growth, e is already a very large number, it's 2.7, right? And something after the decimal point. And then with discrete growth, we have the initial value times 1 plus k, where k is a percentage growth, over t, for example, or x, doesn't matter. the independent variable. And then for continuous growth, you would do E KT. So K is the percentage increase. If you want a 5% increase in discrete growth, you would do whatever A of 10,000 times 1 plus 0.005 to the power of T. So you would have 8 times 0.5 power of T. For continuous growth, you would only have A times E, just this part for K, times T. So if you want a decrease, you would, a 5% decrease, you would signal it here with a minus in front. So it's going to be A times 0.95 T. And if you want a decay in continuous function, you want to just put a minus in front, like this. So please differentiate between these two, because the correct answer would not be 1.05 T, it would be 0.05 T. So the initial value times the growth rate with E. So that's why known details and known in theory very well matters for the statements. Now, again, a tricky task. So here you have the yearly growth rate comparison. And yearly growth is different from semi-annual compounding and continuous compounding. You would need to know something called the effective interest rate that kind of cancels out. It shows you the effects of how often it compounds in a way. You can look it up, and yeah, it's an economic concept that is used quite often, so to say, when you try to compare different savings accounts and so on and so forth to see what's really better for you yearly wise. And then here, usually the more often something compounds, the better it is for you, right? This is like a base rule. So let's say 5% yearly growth would be a bit lower compared to 5% of continuous growth, right? This would give you higher yearly returns as a result. But here we're careful with semi-annual, continuous, and different it's different growth rates, because here's 5%, here's 5.05%. So whenever you're counting for how often it compounds, you divide the percentage by how often it compounds. If it's semi-annual, it's 2, and you also put it to the power of 2, and then minus 1. So it just gives you the percentage of by how much it grows. In our case, for marketing, it's around 5.11316% of growth yearly. So if semi-annual is 5.05%, the yearly would be this. And whenever you're trying to equal out the continuous growth, you would receive 5.7% growth. So for the finance, this is for the marketing. So the yearly growth of the marketing department is actually less. So this is false. So please pay attention to such things. Also, these tasks that I make as updates, whenever I know what kind of skills they were testing, I try to make a task that's a bit more difficult than it would have been in an exam context, because I know that when you're solving the tasks by yourself at home, you're not as stressed, right? It's still not the same. And a bit higher difficulty now would cancel out the stress and the pressure that you would have on the exam day. So like if you're solving a bit of a more difficult task now, it will be actually better, because a slightly maybe easier exam task would feel the same as this one, because you will be solving it in a huge hall with all the people there. You will see your competition in person, and yeah, it equals it out in a way. And here we have again a statement where you have two possible approaches. So to double the revenue compared to the initial value, so to go from 10K to 20K, let's compare how many years the department needs, the finance department needs. So here you have the finance department growth function, and then you just want to see when it's equal to, yeah, to 20K, so to say. There are also shortcut formulas for this. Like you can just also memorize what the the doubling time is. So it's ln of 2 over ln of whatever your base is, the base growth. But if you forget it, because on the exam, of course, the formula can just, it's normal to forget things. You can also just solve it manually from the beginning by plugging in the numbers there. So here you say, okay, you're solving, you cancel this out. And then you should be also comfortable solving logarithmic equations to get the t out. So you need to take ln of both sides. Whenever you're solving an equation, if you do something to one side, you have to do also to the other. It's like twins, you know, if you buy chips for one twin, you also have to buy chips for the other twin, so they don't get in a fight, something like this. And then once you take ln out of them, you put this in front using the properties we learned previously in the other task. And then you have ln of v just equals to 1. So just getting the t out. So to solve for t, that's what you're interested in. And ln of 2 is just a number you can get with the calculator. And then this is a function that the calculator can perform pretty easily. And this is, you're not supposed to calculate this by hand. The calculator will do it for you. And then you have an approximate doubling time of 13.8 years. So yes, the department needs more than 10 years. Or if you want the doubling formula, you can just straight in use it this way. So it's going to be ln of 2 over ln of e 0.05, right? Like this. And that's how you get ln of 2. And ln of e 0.05, it goes in front, divided by 0.05. So this is exactly what we got, just a bit faster in case you remember the formula by heart. In case you don't want to solve for t, but you would just want to see an estimate by plugging the numbers, it's a bit faster. So you say, let's assume it's exactly 10. So if you put t as 10, do we get less or more than 20,000? In our case, we get 16,000, right? So after 10 years, in this scenario, you get 16K, 16 point something. And then to get 20K, you would then logically need more than 10 years. So that's another approach, a bit faster, I would say, that you can use for this task. So you can see, do you prefer the formula way? Do you prefer the working out way? Or do you prefer the plugging in numbers way? So here, the finance, we're comparing the departments now. So the finance department needs 1 year less than the marketing department to make 45K euros. So we say, okay, after how much time will the marketing department and the finance department make 45K? We solve for t using logarithmic functions, like using all the logarithm properties. And long story short, we get to approximately this t values. And as you can see, it's not a 1 year difference, it's less than 1 year difference. So it's not 1 year less than the marketing team, it's less than 1 year less, making the statement false. So sometimes you also have like boarded tasks where you have to reread the statement maybe twice to understand that you're answering it correctly. Also, a nice app I like to use to double check the calculations once you do them. It's Photomaps for studying. You could also use it in case you first do it by hand with your physical calculator and then double check the calculations. Because of course, ideally you should be getting used to pen, paper, and a physical calculator. That's not too complex, like that's not too complex and not too fancy. But of course, now with the preparation, you can double check the Photomath. It also tells you the steps of the calculations. So pretty useful tool. And here, after 10 years, company A will make less than 33K. So here we're doing a joint calculation of two departments in one. So we say, okay, after 10 years, this is what the departments combined together will make. So this is the finance department, this is the marketing department. And this is just a matter of calculating the values. And you say that, yes, it makes a bit less than 33K, making the statement true. So yeah, I hope now the difference between an equation-based task or a functions-based task and a text-based task is clear, and that you're more ready and prepared to approach the statements on exam day. Thank you so much for watching, and see you in the next video. Thank you all for watching. Bye-bye, and subscribe for more.